What goes into making microchips? Microchips are everywhere, and with the advancement of incredible technology, there is a growing demand for efficient microchips, yet they appear to be negligible. Welcome to the Technology Zone, where the home of technologies resides. If you're curious about how microchips are manufactured, we'll go over them in this video. What is a microchip exactly? Microchips are flattened silicon disks with an integrated circuit and even transistors placed on them. By embedding materials into a dense and integrated lattice of linked structures, patterns of small switches are produced on the silicon wafer. The development of these fused circuits involve a number of complex procedures, which we'll go through in detail. Silicon is one of the raw materials. As a widely utilized semiconductor, silicon is the digital gold of the technology sector. Phosphorus or boron are frequently added to semiconductors to improve their characteristics. The good news is that silicon is produced from sand, the second most abundant element after oxygen. Silicon wafers are manufactured from silica sand, a kind of silicon dioxide. The first stage in this process is to melt the sand into a vast cylinder known as ingot. Pure silicon is always a required material from whence the tiny wafers are carved off for microchips. As a result, just one impurity atom per 10 million silicon atoms is permitted. Silicon balls are available in a variety of sizes, with the most popular being 150, 200, and 300 millimeter wafers. Now, silicon wafers for microchips must be very thin. As a result, these wafers are manufactured using a unique sawing process. What is the purpose of a silicon? Silicon is a semiconductor that, when specific circumstances are met, is an excellent conductor of electricity. At ambient temperature, pure monocrystalline silicon is non-conductive because each silicon atom contains 4 outermost electrons. Small amounts of certain particles will be put into the wafer as impurities to make it conductive. This is known as doping, and the most common atoms utilized are boron and phosphorus. The most appropriate elements in these categories have characteristics that are quite comparable to silicon here on the periodic table. The transistors that are also created just on P and N conducting layers are highly crucial, and they are the most critical element of the device. The tiniest control units in microchips are wafer transistors. Controlling electrical voltages and currents is their duty. Because every transistor on a chip has P and N conducting layers, they are by far the most critical components of electronic circuits. These layers are made up of silicon crystals with an extra layer of silicon oxide acting as an insulator. On top of it, an electrically conductive polysilicon layer is applied. What goes into making microchips? The first phase is layout and design. Microchips, which are very sophisticated devices composed of billions of interconnected and coupled transistors that make up complicated circuits like microcontrollers and crypto chips, must constantly be constructed appropriately. A few square millimeters must be adequately measured and delineated. An in-depth design procedure that specifies the chip's functionalities is required due to the precise amount of microcomponents. This describes the chip's physical and technical characteristics. Special design tools are really utilized to create integrated circuit layouts and three-dimensional architecture of sandwiched layers. The geometric pictures of the circuits are created by transferring this blueprint to photo masks. The photographic masks are employed as picture templates during the ensuing chip production process. These patterns would be visible on a microchip to ensure that the tiny features of a chip are accurately duplicated. They must be produced in a dust-free environment with consistent temperature and humidity. Step 2 would be assembling it in a sterile environment. These chips must be manufactured in a clean environment with no more than one dust particle bigger than 0.5 micrometers per 10 liters of air. This facility is incredibly complex, with hundreds of air volume controllers ensuring a steady circulation and several million cubic meters of air cycled per hour. These producing sites have a stringent dress code for their staff. All airlock chips are constructed on this base wafer, which is carved from a silicon ingot according to their size. Because of its tiny size, one wafer may produce several dozen or thousands of chips. The wafer surface is oxidized in a high-temperature furnace at around 1000 degrees Celsius to form a non-conductive layer. Following that, a photoresist substance is evenly dispersed on the non-conductive layer. The coating is subsequently subjected to centrifugal force, which results in forming a light-sensitive layer. The wafer is later exposed to light using a photomask and steppers, special exposure equipment. The circuit designer's intricate geometric patterns are transferred to the silicon wafer using coaster-sized sections of the chip. The chip's pattern's exposed portion is developed, disclosing the oxide layer. The unexposed area remains below as it preserves the oxide layer. The visible layer of oxide in the places that have been created using plasma etching is etched away. A specific gas is bonded to the substrate to also be eliminated in the reaction chamber in this method. Once the photoresist residue has been scraped, the tiny layers in the windows that were revealed and developed in the previous phase can be removed. After the wafer has been cleansed, it is oxidized once again. The photoresist is then applied again after the polysilicon is deposited on the insulating layer. Through the mask, the wafer is exposed to light. The exposed photoresist is peeled again, followed by the polysilicon, and finally the thin oxide layer. Step 3 is the doping procedure. The ion implantation is utilized to incorporate impurity-inducing elements into the uncovered silicon during this operation. The exposed silicon's conductivity varies by fractions of a millimeter as a result of this. After removing the photoresist residue, another oxide layer is deposited, and the wafer goes through another cycle of photoresist exposure via the mask. The stripping contact pores are carved to integrate the conductive layers into the wafer, allowing the contacts and linkages to be integrated. This is accomplished by using specialized equipment to deposit various metal alloys onto the wafer. This improves the microchip's efficiency. Step 4. Apply a smooth finish. After the etching process, the photoresist upon this mask is applied so that the non-exposed strips stay intact. This gives a point of contact with the underlying layers, resulting in a smooth finish on the insulating layer. This necessitates a chemical and mechanical technique that removes superfluous material with micrometer precision. Individual phases in the fabrication process may be repeated several times till the integrated circuit is finished. The wafer will then have multiple dozens to thousands of chips, depending on the size and kind of chip. Individual chips are often scraped out of the wafer, and the chips aren't really aligned flat on the wafer. This is due to the wafer's small bits splintering apart during the sawing operation. As a result, a gap known as the scribe line has always been maintained between individual chips. The scribe line also has structures for taking measurements right after manufacturing. This is just to determine whether the chips are of good quality. Later on, during the sawing process, these unique structures are eliminated. The chips are generally between square millimeters and just a few square centimeters in size. Assembly is the fifth phase. Individual chips are put on a package and terminals are linked during the assembling step. As a result, a thinner semiconductor chip that may be placed on circuit boards using various terminals across many connections is created. There would also be ready-to-use semiconductor components in more extensive packaging for power-related tasks. Trains, electric automobiles, solar cells, and wind generators are just a few semiconductors applications. These semiconductors are designed to convert electrical charges up to a few hundred amps in voltages into thousands. This degree of switching results in extremely high temperatures. The heat must be dispersed through cooling zones included in the packaging. This key feature of semiconductors must be considered throughout the production process. Quality tests for any device are essential to guarantee the effectiveness of such semiconductors. Scanning electron microscopes are frequently used to inspect chips at various stages of the manufacturing process. We can observe how little today's microelectronics are by comparing them to the width of human hair. As a result, the manufacturing procedure for this must be very specialized and flawless. Do you have any knowledge of how microchips are produced? How many of you have seen a microchip? If so, where? Are you familiar with its applications? Please share your thoughts in the section below. Don't forget to like the video and subscribe to our channel, Technology Zone, while you're at it. Also, click the bell button to allow post notifications for more incredible material.